Welcome back. In the last part of this section, we're going to look at derivatives for the log and exponential functions for other bases other than e. This theorem has 4 parts, and really it's kind of 2 parts with a little consequence. The first part tells me how to find the derivative of a to the x. That's just a to the x times natural log of a. The second part, really, it's just chain rule. If we had derivative of a of some function of u, then using the previous part, a to the u natural log of a, that's our derivative with respect to u, and then derivative of u with respect to x. Same thing with 3 and 4. 3 is telling us how to find the derivative of log base a of x. It's just 1 over x times natural log of a. Once we have that, 4 is a chain rule equivalent. If you had log base a of some function of x, you'd say, well, derivative with respect to u would be 1 over u times natural log of a, and then times the derivative of u with respect to x. So for this proof, I'm basically going to prove 1 and 3 because 2 and 4 kind of are automatic consequences of them. So I'll start off with the proof of 1. And for that one, I'm looking for the derivative of a to the x. And so for both of these, for part 1 and part 3, basically what I'm going to use is the definition of what a to the x or log base a is, because those are in terms of e and natural log whose derivative I already know. So if I'm looking for the derivative of a to the x is the same thing as e to the natural log of a times x. And I know how to find the derivative of e to any power. That would be e to that power times the derivative of the exponent. And the derivative of natural log of a times x is just natural log of a. And now we're almost finished because you can see what I've got here is I have natural log of a times e to the natural log of a of x, and we know that e to the natural log of a of x, as we just said, that is a to the x. So we've got natural log of a times a to the x. So that's my proof of 1. I started off by rewriting e to the x as its official definition, e to the power of natural log of a times x, and then I just found the derivative using my exponent rule. My derivative rule for exponential functions. Part 2, I'm going to say that using the part 1's proof that we just did, we've proven the derivative of a to a power, and now this is just a chain rule consequence, so I consider 2 sort of automatically done. I'm just going to say for the proof of part 2, it's using part 1 and chain rule. So now for the proof of part 3. So for this one, we're looking for the derivative with respect to x of log base a of x. And I'm going to do same idea as I did for before. I'm going to use the official definition and say we've defined log base a of x as being natural log of x divided by natural log of a, which is the same thing as 1 over natural log of a times natural log of x. So when we're taking the derivative then, I've got a constant times natural log of x. That constant multiple I'll keep out front. And the derivative of natural log of x is 1 over x. So I get 1 over natural log of a times 1 over x, or 1 over x times natural log of a. And there we go. We've got our proof of 3. And once we've proven 3, then basically 4 is what we just proven in 3 plus chain rule gets us part 4. So now we can use these rules to find the derivatives, and so away we go. So I'm going to do this once with me remembering to know how to do the derivative, and then I'll do it once with me forgetting completely what I'm doing, to show you that there's always a nice workaround. So if you remember your derivative rule that we just learned, I would say, well, for 3 to a power, it would be 3 to that power times natural log of 3 and then I would have to do derivative of the exponent. Derivative of sine squared would be, well, first the power would come down, the power would get reduced by 1. So in other words, 2 times sine times 2 times sine. And then derivative of the inside, the derivative of sine is cosine. So my derivative that I found using just the theorem previously, I can say, well, that should be then 2 sine x cos x times natural log of 3 times 3 to the sine squared x. And this is if I remembered my derivative for 3 to the power of, which is not always a guarantee, and it's nice to have a workaround. One workaround could be, if you remember the definition of writing 3 to the power of in terms of e, you could do that. But I'm going to actually use implicit differentiation as another workaround here. If I knew that f of x was 3 to the power of sine squared, then I know that natural log of f of x is going to be the same thing as natural log of 3 to the sine squared x. And because we know that the log properties will work for whatever power we feel like having, then natural log of 3 to whatever power can now come down in front. And if I were to differentiate both sides with respect to x, then on the left side, I'd have 1 over f of x times the derivative of f, which is f prime. And then on the right side, I would have the derivative of sine squared times this constant. Natural log of 3 is just a constant multiple, so it's not really a product rule that I've got. I'll just leave the natural log of 3 alone. And the derivative of sine squared, power would come down, power would get reduced by 1, and then derivative of sine would be cosine. And then to finally finish things off, to find my derivative, I would bring f of x up to the other side. And then I'd remember that, of course, I know what f of x is. F of x is that original function, 3 to the sine squared. So I get exactly this same derivative that I found before, 3 sine squared times a natural log of 3 times a 2 sine x cos x in some order. And that's exactly the answer that I found earlier. So even if you forgot the derivative of what 3 to the power of, you could still figure things out using implicit differentiation, using actually logarithmic differentiation. Same kind of thing is going to go on for g. I mean, if you remember the derivative for logs of any base, then life is good for you. If not, there's always a workaround. And before I do that, though, regardless of which version I'm going to look at, the remembering the derivative or not version, I'm still going to use my log properties here to make things nicer. Because as it currently stands, I have log of a quotient, and that quotient also involves a chain rule. I really don't feel like dealing with that. So I know you can prove that the log of a quotient for any base is log of the numerator minus log of the denominator, and that for any base you'd be able to take powers out in front. So g could be written as 2 log base 5 of x minus 3 minus log base 5 of cosine of x. So if you remember your derivative for logs of any base, then you're good to go, because you could say that g prime would be, I'll leave the 2 alone. Log base anything of x minus 3 would be 1 over x minus 3 times 1 over natural log of 5, and then times the derivative of x minus 3, which is 1. Minus log base 5 of cosine of x, I'd have 1 over cosine of x. I'd have 1 over natural log of 5, and then the derivative of cosine of x is negative sine of x. And then I would just have a little bit of cleaning to do here, and then I would be finished. For the first little term, I'd have 2 over natural log of 5 times x minus 3. And for the second one, I would have minus and minus giving me plus. Sine over cosine, which I could turn into a tangent, and a natural log of 5 in the denominator. And maybe the one last thing I might feel like doing is taking the natural log of 5 out as a common factor and having just 2 over x minus 3 plus tangent. And that might be where I leave things. So this is, of course, if I remembered my derivative, which is there's no guarantee that you might do that in the heat of the moment. You might remember, and you should hopefully remember, the derivative of natural log, but you might struggle remembering the derivative of all the other logs. So this is where we have an easier time if we maybe think about first taking g of x and rewriting it again. I already rewrote it once in terms of splitting it up, but we also know we have the change of base formula. So when I say log base 5 of x minus 3, that is natural log of x minus 3 over natural log of 5. And same thing with the log base 5 of cosine of x. That could be turned into natural log of cosine divided by natural log of 5. And in doing so, now I've kind of made my life a little bit easier for myself. I've kind of rewritten things as I went along. The over natural logs of 5, I brought them out front because I know natural log of 5 is just a constant multiple. And now finding the derivative, I'm going to get the same answer as before, but maybe a little easier, and I don't have to stress so much. Derivative of natural log of x minus 3 would be 1 over x minus 3. The derivative of natural log of cosine would be 1 over cosine times derivative of cosine, which is negative sine. And you can see we're going to get exactly the same result at the end of it all. We're going to have 2 natural log 5 times x minus 3. The minuses will cancel to give us a plus. Sine over cosine will be tangent. And we'll have natural log of 5 in the denominator. So we get exactly the same result that we did the first time. Just this way, I don't have to remember the other log derivatives. And that I think is a kind of nice way to be. So if we're thinking about the integration side of things, if you're thinking about integrating a to the x, I mean, we know for a to the x when we differentiate it, a natural log of a is multiplied, so not a big surprise that if you're finding an antiderivative, you would be dividing by natural log of a. So you can convince yourself 1 over natural log of a times a to the x. If you differentiate that, constant will stay alone. For a to the x, you'd have a to the x times natural log of a, and the natural log of a's would cancel. So derivative of this expression is a to the x. So an antiderivative for a to the x is that expression. So there we go. For an antiderivative for a to the x, it's 1 over natural log of a times a to the x. I have a little definite integral I want to do here. It's evaluating this definite integral of 3 to the power of, going from pi over 6 to pi over 2. And I'm going to notice I need to do a little bit of a substitution, as I would for exponential function base e as well. I see I've got a cosecant x, and I've got for outside, there's a cosecant cotangent, so I'm feeling like a pretty obvious choice of letting u be cosecant. So du would be negative cosecant cotangent. And that means that negative du would be what I'd be using to replace cosecant cotangent. Of course, I also need to take care of my limits of integration. So as far as x is going, we're going from pi over 2... pi over 6 to pi over 2. So now we need to figure out what's happening for u. When x is pi over 6, u would be cosecant of pi over 6, which turns out to be 2. And when x is pi over 2, cosecant of pi over 2 is just 1. So again, this is the sort of same warning that I gave before. The tendency is for us to always write our limits from smaller to larger numbers, but be careful here. If x is going from pi over 6 to pi over 2, then u will not be going from 1 to 2, it'll be going from 2 to 1. So my definite integral in terms of u would be going from 2 to 1, and it would be, instead of 3 cosecant x, it would be 3 to the u. And cosecant cotangent dx, all of that is taken care of with the negative du. And so now all I need to do is clean things up by finding my antiderivative, and I know what that is. That is 3 to the u divided by natural log of 3. And I'm going to be evaluating this between u equals 2 and u equals 1. So away we go. We're going to start off by evaluating at our upper limit. So that would be 3 to the 1 over natural log of 3. And then evaluating at my lower limit, that's 3 squared over natural log of 3. So you'd have 3 minus 9, that's negative 6. The negative out front would now make it a positive 6. So it looks like I get positive 6 over natural log of 3. And there we go. That's my definite integral for this function. Okay, now we're kind of getting to something that's kind of fun here. We have finally our proof that the power rule, we can now feel convinced and good about using it whenever we feel like. So we want to show for any real number n that x to the n's derivative would be n times x to the n minus 1. And the proof for this is actually not really that hard. It's going to just involve logarithmic differentiation, actually. But it took to this point because we had to be able to convince ourselves that an exponential function with a real power had some sort of a meaning. In other words, what does x to a real power even mean? Well, now we have a way of thinking about what that means. So I can feel good about now the following. I can say, well, if my function was x to the n, then I know that natural log of f of x would be natural log of x to the n. Now, you might be worried about, well, what if things are negative? And I'd say, well, that's fine. I can just put absolute values on things, right? Because if f of x is x to the n, then absolute value of f of x would be absolute value of x to the n, and natural log of absolute value of f of x would be natural log of x to the n. Probably not too surprising if we're thinking about this, if you're thinking about x to the n and then taking absolute value, that would be the same thing as if you were to take absolute value and then raised it to a power of n. So essentially we could rewrite it like that. Now I'm able to use my log properties. We didn't go back and reprove things, but since we've now convinced ourselves about how real exponents make sense, then our earlier log property of natural log of something to a power, allowing our power to come down in front, that would actually apply for any real power now, not just rational powers. And now I'm going to differentiate both sides with respect to x. And on the left side, remember for natural log of absolute value, the absolute value doesn't pop up in the derivative. It would just be 1 over f of x times f of x's derivative, which is f prime. For natural log of absolute value of x, its derivative is the same thing as just regular old natural log of x, which is 1 over x. And now we're almost finished, because if I were to bring f of x to the other side of the equation, I'd have f prime is n times 1 over x times f of x, and f of x is x to the n. And x to the n and x on the denominator cancel out, giving me n x to the n minus 1. So now I can feel confident in this, and I can now be happy about saying the power rule applies for any real exponent. You might also notice that me being able to clean things up here and saying x to the n over x to the 1 is x to the n minus 1. The reason I can do that now for any real exponent is because the exponential properties now work for any real exponent. So I don't have to worry about, oh, well, what if n was not a rational number? Would I be able to use those exponent properties? The answer is yes, I can. Okay, one last little thing to look at, which is this is a limit that you probably would have seen back in pre-calculus days, but it was usually just explained with sort of a trust me, or maybe with calculators. You plugged in huge numbers for n, and you saw that as n got large, you seemed to be tapering off to this funny constant 2.718 and so on. It would be nice, though, if we were able to prove this. So what I'm going to do is I'm just going to, so I don't have to keep writing it down, I'm going to let k be the expression that we're talking about, 1 plus 1 over n to the n. So if we're looking at our limit as n goes to infinity of 1 plus 1 over n to the n, that's me just looking at my limit as n goes to infinity for this mystery function k. So I'm thinking about k being this function. And so the limit of that function, whatever we get as n goes to infinity, is whatever k is going to as n goes to infinity. Okay, so you might be saying to yourself, that's interesting, but so what? Well, I mean, for the right side of the equation, no matter what n is, we're going to be getting very large for n. So this is going to be some sort of positive number. This will be some sort of positive number to some sort of positive power. We can easily convince ourselves, no matter what number n is, if n is getting to be large, this is going to be something bigger than 0. So we can definitely take a natural log of both sides of the equation. If k is equal to all this stuff, then I can also say that natural log of k should be natural log of 1 plus 1 over n to the n. And so now I'm going to say to myself, well, I can really rephrase this as n times natural log of 1 plus 1 over n. So originally I wanted to know what happened as n went to infinity for this expression. If this turns out to be some sort of finite number, if this limit turns out to be some sort of finite number, then natural log of will also be a finite number. So that's kind of my plan here, is sort of a workaround. I'm going to figure out what happens to natural log of k as n goes to infinity. What happens to this expression as n goes to infinity? And if I find out that natural log of k will go to some finite number, then I can figure out what k will go to. So the problem that I'm going to have here, though, is if I start looking at the limit as n goes to infinity of n times natural log of 1 plus 1 over n. Right now, n is going to infinity, and as n goes to infinity, 1 over n is going to go to 0, which means this is going to go to 1 plus 0, which is 1, and natural log of 1 is going to 0. In other words, we're going to something very indeterminate, infinity times 0, which is not something I want to have. So now I'm going to say to myself, well, maybe I could rephrase this a little bit and rewrite this as perhaps natural log of 1 plus 1 over n. Instead of n in the numerator, I could make it divided by 1 over n, because if we divide by 1 over n, that's the same thing as multiplying by n. So these two things are equivalent to each other. Just now, instead of being infinity times 0, now the numerator is going to 0 and the denominator is also going to 0. Again, this is still indeterminate. So I'm going to do a little bit of a switch around here. So instead of me talking about things going to infinity, I might take a little notice to myself that if I were thinking about u being 1 over n, then as n goes to infinity, so as n gets to be infinitely large, u is going to be getting close to 0. And in fact, it's going to be getting close to 0 through positive values. So, in other words, if I have this limit in terms of n's, I'd be looking at it with n going to infinity. But if I replace all these 1 over n's with u's, then I'd be looking at the limit as u goes to 0. So, okay, let's do that. So this is limit as u goes to 0 of, instead of natural log of 1 plus 1 over n, it's now natural log of 1 plus u. And in the denominator, instead of 1 over n, it's now u. And you're probably saying to yourself, okay, well, how does that help us? And I'm going to say, well, this maybe doesn't look like something super familiar just yet, but we remember that natural log of 1 is 0. So hopefully nobody will be upset if I were to add on a natural log of 1 into the numerator, or subtract a natural log of 1 for that matter. So in other words, I could plop that in no problem. And you might say to yourself, okay, why are you plopping this in with no problem? I mean, nobody's going to be upset about this. These two things are definitely equal to each other because we certainly do have top and bottom, the top being the same. Natural log of 1 is just 0. I've subtracted 0. But I would ask you this question, if instead of me using a u going to 0, if I had used a delta x going to 0, and you saw a natural log of 1 plus delta x minus natural log of 1 over u, so in other words, if you saw a limit as delta x goes to 0, natural log of 1 plus delta x minus natural log of 1 over delta x. Hopefully at this point in the course you will say, wait, that's a difference quotient. That would be the derivative of natural log at x equals 1. In other words, that is the derivative of natural log of 1. And we know how to find that. We know what the derivative of natural log of x at x equals 1 is. The derivative of natural log of x is 1 over x, and when x equals 1, we get 1. So that's my little answer for what is this limit. This limit turns out to be 1 because what we've actually been building secretly underneath it all turned out to be a difference quotient. So that's my justification. Essentially what we have here, this is the difference quotient for natural log evaluated at 1, or in other words, this is the derivative of natural log at 1, and the derivative of natural log at 1 is 1. Okay, so we found the answer to part of our problem, but what did we actually find? Backtracking, what we were looking at was the limit of n times natural log of 1 plus 1 over n. We did all that work and we showed that that limit is 1. In other words, we were looking at the limit for n goes to infinity for natural log of k. So what we've actually just concluded now is for k, as n goes to infinity, natural log of k goes to 1, so probably no surprise if natural log of k is going to 1, well then what should k be going to? It should be going to e to the 1. And so there we go. We can feel confident now that this limit that we had, the limit 1 plus 1 over n to the n going to e, now we can feel happy and say, yeah, it definitely is e. It's e to the 1. And that was because when we looked at log of that log of that limit was going to 1. So the limit itself must have been going to e to the 1. So there we go. Because this natural log goes to 1, then the original thing goes to e to the 1, and therefore we've now established our limit for e that we must have seen back in pre-calculus days.